In this presentation, I'll be explaining triangular and sawtooth waveform generation using operational amplifier. Now let us see triangular wave generator. How can you generate triangular waveform using operational amplifier? And in there are two methods in which in first method we'll be generating a square waveform, and that square waveform is given as an input to an integrator. Therefore, when a square waveform is integrated, you will be getting a triangular waveform. That is the one method. The second method is we'll be using a two-level comparator that we'll be seeing next slide. A two-level comparator will be using, and the output of the two-level comparator will be giving to an integrator. Therefore, there are two methods of generating triangular waveform, in which let us see the first method, in which the first one, this is a square waveform generator, and the output of the square wave that is given to an integrator circuit. And therefore, here the square wave output will be either plus Vsat or minus Vsat. That is plus Vsat or minus Vsat is output waveform of the square waveform. And as already we have seen a stable multi-vibrator using the op-amp circuit, in which we can generate a square waveform output, and the output frequency is given by 1 by 2 pi RC into natural logarithm of 1 plus beta divided by 1 minus beta, in which R value is the feedback resistance and C is the capacitor which is connected to the non-inverting input, inverting input, that is an inverting input capacitance. And here the beta value is a feedback factor, which is the ratio of the R2 divided by R1 plus R2. Therefore, as per this equation, you can calculate what is the output frequency of this square waveform. And this output of the square waveform you are giving to an integrator, in which this integrator, the resistance here at the R3 and then R4, and this is a, of course, there is a feedback capacitor that is given here. And the purpose of introducing R3, this R4 in the feedback path is that if at all there is a DC input, DC shift is coming at the input, if there is, in the absence of that one, that will be causing to integrate this op-amp into saturation, and that's in saturation, so that the working will not be perfect. And in order to avoid this one, we will be connecting a resistor R4 in parallel with this capacitor, so that the DC quantity that is at this one will be getting that will be amplified, and the AC part will be getting integrated. That is the purpose of adding a resistance. It's already explained in the case of a practical integrator. Therefore, this is a square wave generator. Output of the square wave generator is given to a practical integrator, and the output waveform is having a frequency, as I explained, 1 by 2 pi RC natural logarithm 1 plus beta divided by minus beta, and that is given as input to the integrator. Integrator output is given by minus 1 by this resistance at the input side, R3 into this C2 integral this what is, if you write as V0 dash dt. Therefore, this is the output of this integrator. That will be a triangular waveform. Therefore, this is the output of the square waveform with a time period t given by this one, and this is the integrator output, which is a triangular waveform. Therefore, the amplitude of the square waveform is either plus or minus Vsat. It will be either plus Vsat or minus Vsat, but the amplitude of the triangular will be decreasing as the frequency increases. This amplitude will be decreasing, because that is frequency. As frequency changes, this reactance will be changing. Therefore, the output magnitude of this triangular waveform will be decreasing as frequency increases, because the reactance of the feedback capacitance of the integrator decreases at high frequency. That is why this amplitude of this triangular signal decreases as frequency increases. Therefore, the output frequency, as I already explained, is equal to 1 by t, 1 by 2 pi RC natural logarithm of 1 plus beta divided by 1 minus beta. Beta is the R2 divided by R1 plus R2. And the output voltage is given by integral of this V0 dash, that is V0 equal to minus 1 by R3 into C2 integral V0 dash dt. That is a triangular output. Second method of triangular wave generator, that is using a two-level comparator. That is, this is called a two-level comparator, and the output of the two-level comparator that is given to an integrator, Therefore, a two-level comparator plus integrator, that is another triangular wave generator configuration in which there are two op-amps, but this uses less number of components. This consists of a two-level comparator followed by an integrator. The integrator will be the output, and here will be a square waveform that is integrated, and you will be getting the output triangular waveform. Now, let us see the working of that one. Output of this comparator, that is that this is the A1, it is noted, and this is A2 is noted. Then output of the comparator A1 is a square wave. Either it will be plus Vsat or minus Vsat, and it is applied to the negative input terminal of an integrator. This is given to a negative input terminal of the integrator, which is the A2 integrator op-amp A2, producing a triangular waveform. This triangular waveform is, that is this output triangular waveform is known, that is feedback, to the triangular waveform is fed back as an input to the comparator A1 through a voltage divider, that is R2 R3. This is R2 R3 is a voltage divider, R2 and R3, and this end is the output of this triangular signal, and here the output is the square wave. Therefore, that is voltage is divided, and that output is this point voltage, that point P, that is connected to the non-inverting terminal of the comparator A1, and the inverting terminal of the comparator is grounded. Therefore, this is a two-level comparator, and output of the two-level comparator is integrated, and integrator output is given as the one of the input of this voltage divider circuit, and our input is the output of V0 dash, output of the square wave generator, and this midpoint is connected to the non-inverting terminal. Therefore, that is the configuration of a two-level comparator plus an integrator. Basically, it is called a triangular wave generator. Output you will be getting a triangular waveform. And assume initially the output of the comparator A1 is a plus V. First, we assume that output of the comparator, that is V0 dash, is equal to plus Vsat, and output of the integrator is a negative going ramp starting from plus V ramp. That is, here I initially just to assume that plus here equal to plus Vsat, is plus Vsat, and here the output is a, because we are connecting to input to a minus terminal or a non-inverting terminal. That is why we will be getting a negative slope as such. Here that will be integrated with a plus V ramp. This voltage, the maximum voltage at which it is changing is plus V ramp and minus V ramp. From plus V ramp, it is going having a negative slope. This negative is because of that is, since we are applying to the negative terminal, we are getting, even though positive is voltage is positive, the equation is equal to minus 1 by this resistance and capacitance into integral this voltage. So there's a minus sign is there. Due to that one, even though the voltage is positive, they will be getting a negative slope. Therefore, this is the case when the output is equal to plus Vsat. The output of the triangular voltage is changing from plus V ramp to the minus V ramp. Continuing the triangular wave generator using a two-level comparator plus integrator. Now, one end of the voltage divider, that is this one end of this voltage divider, the formed by R2 and R3. This is R2 and this is R3. One end will be plus Vsat, because we are assuming that first it is equal to plus Vsat. This will be plus Vsat, and at the same time, this one that is will be changing like this one. This is the voltage that is coming during this period. That is the voltage at this one. That is not a fixed one. That voltage is changing from plus V ramp to minus V ramp, and the other end at a negative going ramp. This is a negative going ramp voltage that is at the A2. That is, you will be getting other end here will be getting from the A2 a negative going ramp is coming at this end, and here you will be getting plus Vsat. Now there are two voltages. What is the voltage at this point? Again, you have to apply the superposition theorem. Now, at time t equal to t1, say at any time t equal to t1, the negative ramp attains a value minus, that is, in this case, this is the time at we can marking it as this is equal to the it is marked as t equal to t1. It is marked as at time t equal to t1. This negative ramp is attaining a magnitude of minus V ramp. It is getting a magnitude of minus V ramp, and the effective voltage at the point P, that is at this point when it is coming minus V ramp, what is the voltage at this point P? That can be obtained by using the superposition theorem. That is, P during the time when the output A1 is at plus Vsat, at the time t1 can be found out using the superposition theorem. You can apply the superposition theorem. Therefore, at time t1 means at this instant, the voltage at this point is equal to minus Vram, and the voltage at this point, just at that point, just before that one, we'll getting plus Vsat. Now, just analyze what is the voltage just before the transition at this point P. Therefore, the voltage at point P is equal to just before the transition here. The voltage due to plus Vsat is given by Vsat into here R2 by R3 into R2 by R3 into R2, then minus, here the voltage is minus Vram into, this is grounded. We are assuming this is a grounded. We are minus Vram into R3 divided by R2 plus R3. R3 divided by R2 plus R3. Therefore, this is the equation for the voltage at point P when this voltage equal to minus Vram and when this voltage equal to plus Vsat. By applying the superposition theorem, the voltage at the point P is calculated as this one. At time t equal to t1, the voltage at P becomes just below, that is, as this voltage is going just below the zero voltage, just going below the zero, and the output of the comparator changes from plus Vsat to minus. As this voltage is going just below the zero voltage, or this voltage is going just above that one, then output will, from here it will be changing from plus Vsat to the minus Vsat. That is why we are equating this one, the voltage at this point, just we are equating to zero. The instant at which this is just coming zero, just below zero, that will be changing. That this voltage is coming just below zero, this will be changing to minus Vsat. Therefore, we are equating this one to zero, and then we'll be getting plus Vsat into R2 divided by R2 plus R3 minus Vram into R3 divided by R2 plus R3. That is equated to zero, and then we'll be getting the equation from this equation minus Vram equal to R2 by R3 into Vsat. This is the first equation derived at the condition when this voltage is going just below zero. At that point, there will be a transition from plus Vsat to minus Vsat. Continuing the two-level comparator plus integrator. And in that what we have seen that at this instant, when the voltage at this point is going just below zero, and so here it will become changing from plus Vsat to minus Vsat. That is this instant. Output is changing from plus Vsat to minus Vsat. After that one, that is then after this point, here it will become minus Vsat. Then when you are integrating, it will be having a negative voltage. Therefore, it will have a positive because we are applying a negative input. That is why the output of this will have a positive slope. That is why here the output of this integrator will be having a positive slope. That will be changing from minus Vram until plus Vram. That is, the output of the integrator is changing here from minus Vram to plus Vram. And now let us, what is the voltage at this instant? At the instant of, say, integrator output voltage will have a positive slope starting from minus Vram. And similarly at T2, we are analyzing at T2. At T2 also, we have to have a transition. The transition will be taking place when this voltage is going just above this voltage. Just, that is, when just above, in the sense, this voltage is going just above zero voltage. As this voltage is going just above zero voltage, then here it will become changing to plus Vsat. That is this transition taking place at this instant T2. Therefore, you have to calculate what is the voltage in the second case. At time T2, what is the voltage coming at the point P? Then that is to be equated to zero. Then you can get the second equation. Therefore, at the point P, again you have to apply the superposition theorem. Here the voltage equal to minus Vsat, and here the voltage is equal to plus Vram. Here the voltage equal to plus Vram, and here the voltage is equal to minus Vsat. Again, you have to apply the superposition theorem. Therefore, minus Vsat, that is this voltage, into or divided by R2 plus R3 into R2. R2 plus R3 into R2. Then plus Vram. This is the voltage that is coming. This is grounded. Plus Vram divided by R2 plus R3 into R3. R2 plus divided by R2 plus R3 into R3. Therefore, this voltage is just crossing the 0 point, means that we will be equating again to 0. And from this second equation, again you will be getting plus Vram equal to R2 by R3 into Vsat. Therefore, you got this is the second equation. Therefore, the first equation you got by equating this one to 0 at this point, and second equation you got what is the voltage at this point P, that is equal to just 0. Then you got the second equation. Now, then you can calculate VRAM plus VRAM you got as well as minus VRAM you got. Then you can calculate what is the peak to peak value of this VRAM. Here, that is we call it as V out. That is the VRAM means this is a signal, that is a triangular signal you are getting. Therefore, output voltage peak to peak, that is from here to here. That VRAM minus VRAM, that is 2 minus 1. That will be getting, it is equal to VSAT into here R2 by R3. Here R2 by here you will be getting R2 by R3 minus again R2 by R3, or here minus R2 by R3. Here is a minus sign is here R2 by R3 we said. Previously there's a minus sign is the R2 by R3 minus R2 by R3, or they will be getting 2 times R2 by R3 into VSAT. 2 R2 by R3 into VSAT. That is the this voltage. That is the voltage VRAM minus VRAM. That is the peak to peak voltage of this output triangular signal is given by 2 times R2 by R3 into VSAT. This is a basic equation relating output voltage peak to peak voltage, because output voltage is a triangular voltage. What is this peak to peak voltage? VRAM is this and this is a minus VRAM. What is this difference in voltage, which is equal to 2 times R2 by R3 into VSAT. This is R2 and this is R3. Therefore, output will be after that, after reaching this one, that is after just going above 0, this will be output will be again changing from minus VSAT to plus VSAT. That is the output switches from after this one output switches from plus VRAM to minus VRAM, and vice versa half of the time. That is this changing from plus VRAM to minus VRAM or minus VRAM to plus VRAM. This change is the half of the time, because this is a total time period. During the half the time period, the output of the integrator is changing from plus VRAM to minus VRAM. Again, next half minus VRAM to plus VRAM. So this is the total time period. Now this output voltage peak to peak value is equal to 2 times R2 by R3 into the saturation voltage VSAT of the this op-amp A1. Now continuing the two-level comparator plus integrator configuration of a triangular wave generation. This is a square wave is generated here, that is integrated, then you will be getting a triangular waveform, and this is the square wave output, that is the V0 dash, and this is the output of the integrator that is oscillating from plus VRAM to minus VRAM, and that magnitude already we derived 2 times R2 by R3 into VSAT, that is already we derived, that is here 2 R2 by R3 into VSAT. Now the integrator output can be, again there's one more equation for finding out the integrator. Integrator output equation, basic equation is output voltage is given by minus 1 by, this is R1 and this is C1, minus 1 by R1 into C1 integral, that is 0 to T by 2. This total is T, or integral 0 to T by 2, and here I am taking it is equal to minus VSAT. Therefore, I am taking that minus VSAT, or we can take either minus, if you are either minus or positive VSAT, or minus VSAT I am taking, or then this output voltage peak to peak voltage, if you integrate this one, we'll be getting VSAT divided by R1 C1 into T by 2. Already we have derived for the peak to peak value of the output voltage 2 R2 by R1 into VSAT. You can equate these two equations, like this is the output of the integrator based on the basic equation of the output voltage of an integrator, minus 1 by R1 C1 integral 0 to T by 2 minus or VI dt or minus VSAT into dt. Therefore, equating these two things, equating this one and the other one, that is V0 P, and this one as well as this 2R2 by R1, equating these two, you will be getting the time period T equal to, that is time period of this one, total time period of this triangular signal, that is from this equation. If you reduce it one, you can get it is equal to 4 times R2, here 4 times R1 R2 C1 divided by R3. It is equal to 4 times R1 R2 C1 divided by R3. That is obtaining from this equation. Once you get the time period, you can calculate the frequency, which is equal to 1 by capital T or 1 by T, which is equal to R3 divided by 4R1 R2 C1. Therefore, this is the equation of the triangular signal frequency. But the signal output of frequency of the triangular signal is given by R3 divided by 4R1 R2 C1, where this is R2, this is R3, and this is R1, and this is C1. So this is the output frequency equation of a two-level comparator plus integrator, in which you are getting a triangular output which is oscillating from plus VRAM to minus VRAM, and the total time period is calculated as this one, and the frequency is equal to 1 by T, which is equal to R3 divided by 4R1 R2 into C1. Continuing a two-level comparator integrator problem is discussing, in which the design a triangular wave generator with the following specification. What all things are given? Output frequency, required output frequency equal to 2 kilohertz. We want to have a 2 kilohertz output triangular signal, and the it is to be varied from V0 peak to peak equal to 7 volt. Means that plus 3.5 to minus 3.5. Peak to peak voltage of triangular signal equal to 7 volt. And VSAT, that is VSAT here, that is equal to 14 volts. And assume that R2 is we are assuming this R2 equal to 10 kilo, as well as the feedback capacitor C1 equal to 0.05 microfarad. You are asked to find out other parameters like what should be the R3 and what should be the R1. This is to be designed. Then in order to get an output triangular signal having the frequency 2 kilohertz and peak to peak value of 7 volts. Now coming to that equation, coming to the solution here, peak to peak value V0 peak to peak, already we derived the equation in terms of R2, R3 and VSAT. It is equal to twice R2 by R3. Twice here we'll be getting twice R2 by R3 into VSAT. That is given as 7 volt. Therefore, in this one, 2 times R2 is given in the problem. It is taken as 10 kilo ohms. 2 into 10 kilo ohms divided by R3 into VSAT is given as 14 into VSAT. That is equal to 7 volts. That is equal to V0 peak to peak, that is equal to 7 volt. From only unknown is equal to this R3, that is this resistance. R3 is the only unknown. Then you will be getting it equal to 40 kilo ohms. Therefore, this resistance is equal to 40 kilo ohms and this is already equal to 10 kilo ohms. Then this capacitance is already given. It is equal to 0.05 microfarad. Now you have to find out, in order to get an output frequency of 2 kilohertz, what should be this value of the resistance R1? That is the question. Therefore, the output frequency equation, as we already derived, it is equal to 1 by T, which is F0, it is equal to R3 divided by 4 R1 R2 into C1. R3 divided by 4 R1 R2 into C1. R3 we calculated is equal to 40 kilo ohms divided by 4 into and we are calculating R2 is substitute. R2 is equal to 10 kilo. We are substituting. Only the unknown is R1 C1 is the unknown, the product R1 C1. From this equation, you can calculate what is R1 C1. It is the actual time constant of the integrator. We will be getting it is equal to 0.5 milliseconds. That is the time constant of the integrator. And in this one, C1 value is given. Then only unknown is equal to R1. You can find out what is the resistance that will be connected to the input of the integrator. And that you will be getting it is equal to 10 kilo ohm. Therefore, if you select a R1 equal to 10 kilo ohm and the R3 is equal to 40 kilo with the given value of the capacitance as well as the R2, and this much you'll be getting a triangular signal having the peak to peak of 7 volts as well as output frequency of 2 kilohertz. That is by using a two-level comparator plus integrator. This is a two-level comparator. Output of the two-level comparator is given to an integrator, and the output frequency equation is given by R3 divided by 4 R1 R2 in C1. Next we will be seeing Sawtooth wave generator. The difference between a triangular and a sawtooth wave generator is that the rise time and the fall time of a triangular waves are equal. In the case, considering if you take a triangular waveform, the rise time and fall times are both are equal. Therefore, in the case of a sawtooth case, that is the different. Time taken for the rise time is not same as the time taken for the fall one. In the case of a sawtooth case. Therefore, the time taken by the triangular wave to swing between plus VRAM to minus VRAM is same as the time taken for the change from minus VRAM to plus VRAM in the case of a triangular signal. What I'm telling, this is the case in the case of a triangular signal. But in sawtooth one, in order to change from plus VRAM to minus VRAM, it is taking this much time. But in order to take from minus VRAM to plus VRAM, it is taking more time. Therefore, the rise time as well as the fall times are different for a sawtooth case. Therefore, on other hand, in a sawtooth waveform, these are unequal. That's the main difference. In a triangular waveform, here the both fall time as well as the rise times are equal, so that the time required to change from plus VRAM to minus VRAM or minus VRAM to plus VRAM both are equal. But in the case of a sawtooth waveform, these are not equal. That is seen from this diagram. And this is a sawtooth waveform in which this is plus VRAM to minus VRAM. It takes this much time only. From minus VRAM to plus VRAM, it takes more time. Therefore, this is a sawtooth waveform. Now, let us see how you can generate a sawtooth waveform. Small change in the addition in the triangular waveform. For the this is a two-level comparator, and the output of the two-level comparator, of course, there is a Zener diode is connected to seal that voltage. That's the only purpose of that one. That is, and the output of that one is given to an integrator. An integrator here, previously the integrator, this point was grounded through a compensating resistors, but rather than grounding here, we are applying a voltage through a potential divider circuit like plus VCC and minus VCC. You can adjust this voltage that is applied to the non-inverting terminal so that this fall and rise time can be adjusted. That's the only change. This is the only change in the compared to the triangular signal. Only the voltage, rather than applying a ground voltage through a compensating resistor here you are applying a voltage, variable voltage through a potential divider circuit that is varying from plus VCC to minus VCC. Continuing the sawtooth waveform circuit is, as I already explained that one. So a triangular wave generator can be converted into a sawtooth wave generator by applying a variable DC voltage into a non-inverting terminal of the integrator. Only this is the change. We are applying a variable voltage to the non-inverting terminal so that you can change this fall time as well as rise time. And this can be accomplished by using a potentiometer and connecting to plus VCC and minus. Here it is connected to the plus VCC as well as minus VCC, and by changing this potential at this point, you can vary the rise time and fall time of the output signal, triangular signal. And if the rise time is not equal to the fall time, you will be getting a sawtooth waveform. And this is what is shown here. This is the fall time. That is this much only the time to required to change from plus VRAM to minus VRAM, and this much time is required to change from minus VRAM to plus VRAM. And this output is the output available at this one that can be obtained by changing this voltage that is applied to, by changing the voltage applied to the non-inverting terminal. Therefore, that is the change in the case of sawtooth waveform compared to the triangular. All others are same. The two-level comparator is there, an integrator is there. Only thing is that this voltage is a variable voltage that will be varying from plus VCC to minus VCC. Therefore, depending on this can be accomplished by using a potentiometer connecting to plus VCC and minus VCC. Depending upon the settings, this is depending upon the settings, the rise time and fall time can be adjusted. Now let us see the effect of slew rate on the waveform generation, because we have seen how we can generate a triangular signal, sawtooth signal, etc. But the slew rate of op-amp has a certain effect on that one. Now slew rate, as you saw, that slew rate is the maximum rate of change of output voltage, that is permitted rate of output voltage. That's maximum dV out divided by dt. That is what is the slew rate. For slew rate is the maximum rate of change of output voltage per unit time. That is the definition of the slew rate. Therefore, for a particular op-amp, it has got a certain value of the slew rate, and unit is equal to that much voltage per microsecond. It is the voltage, or sometimes voltage per millisecond. Anyway, the unit is that your numerator will be voltage, denominator will be in time. Therefore, voltage per microsecond. For the slew rate of an op-amp is particularly important parameter in the application where the output is required to switch from one level to another quickly. If you want to change the output from plus VSAT to minus VSAT or minus VSAT to plus VSAT suddenly, that is then the slew rate of the op-amp is very much important. Therefore, if you see, because of the practical case, if an op-amp is operated with a certain value of the slew rate, its slew rate limit signals will be distorted. If the op-amp is operated above its slew rate, that is, if the voltage is suddenly changing above this permitted value or the value of the slew rate of the op-amp, then we can see that one. This is the actual, ideal what we want to change from minus VSAT to plus VSAT or plus VSAT to minus VSAT, what we are expecting. But because of the slew rate of the op-amp, rather than changing like this one, it will be changing some delay is taking. Therefore, the voltage is changing from this one to this one. This is the actual, what is shown as the actual waveform is this one. This is the actual waveform. This actual waveform is because of the slew rate of the op amp. This is the ideal one. This is the ideal one, and this is the actual waveform. Therefore, the distortion of the square waveform is due to the slew rate of the op amp. That is 0.5 volt per microsecond is for a IC. Op amp ICs, if it is that one, that much time will be taking. As that much for that time, the maximum permitted value of the change in voltage is that much, 0.5 volt per microseconds. And if the voltage is changing, the operating is more than this slew rate, then output voltage gets distorted like that one. That is the effect of the slew rate on the shape of the output waveform. That is the effect of slew rate on waveform generation.